Okay, so good afternoon, good morning, everybody. So today it's a pleasure to welcome Professor Mehdi Vahdati. So I will make a short introduction. So Professor Vahdati is a principal research fellow in the thermo-fluid division. He has over 30 years of experience in developing numerical models for aerodynamics and aeroelasticity. Prior to this current position, he led the Aeroelasticity group at Rolls-Royce Vibration University Technology Center at Imperial College. During this time, his group developed the aerodynamics and aeroelasticity code AU3D, which is used at all Rolls-Royce sites in UK, US, Germany, or India as the only code for aeroelastic analysis. So every Rolls-Royce engine since the late 1990s has utilized this code during its development, including the entire train engine family. This has led to considerable saving for Rolls-Royce. So he was awarded the position of Rolls-Royce Research Fellow in Imperial College, the first person to receive this award for his services to the company. He has been a partner in major UK and European turbomachinery projects. His research topic includes development of CFD algorithms for internal and external flows, development of numerical aeroelasticity models, aeroelastic modeling of gas turbine components, fan, compressor, turbine, and seals, turbulence modeling using machine learning, application of machine learning in turbomachinery, aerodynamics and aeroacoustics modeling of drones, aeroelastic behavior of wind turbine, and many others. So it is our pleasure to welcome Professor Vahdati for this LMFL webinar. And now I will stop sharing and I will give him the right permission to share his. Let me check. Okay, I stop sharing. So now you should be able to share. Yes.
I see.
Okay. So please go ahead.
Let me minimize that and maximize that and continue meeting. Yeah. Thanks very much for your kind introduction, and thank you everyone for coming to this meeting, this presentation that is going to be about computational aeroelasticity of turbomachines. Originally, I was going to give a larger presentation which covered all aspects of aeroelasticity. However, due to limitation in time, I've just divided into two parts, and I'm hoping to do part two later on in the year. And in the first part, I'll just be looking at Flutter, which is one of the common problems in turbomachinery. I've shown a picture of an aero engine here, and obviously aero engine is a kind of turbo machine, but the concepts that I'll be showing today and in a later lecture would be applicable in most forms of turbo machinery, such as industrial gas turbines or steam turbines. So, but today I will be mainly focusing on Flutter. Okay. So the outline of my presentation today is, first of all, I'm going to give a brief description of what is aeroelasticity. I'm not just going to go too much in the theory, and I just try to give some basic concepts of aeroelasticity. And then I explain the aeroelastic phenomena, i.e. today, Flutter, using a 2D aerofoil. And I think because this is a fluid mechanics lab, and obviously aeroelasticity involves fluid-solid interaction, I give some basic mechanical vibration concept, which is important to know before you move to aeroelasticity. So you can see how air and structure interact to give you different aeroelastic phenomena. Then I'm going to introduce the computational aeroelastic model that I've used in this work. And most of the results, and then finally, I'm going to show application. And the application would be Flutter modeling of fan blades in aero engines. Most of the work I show, as the title suggests, is computational and have been done using CFD. But whenever it was possible, I'll gather some measured data to compare against measured data to see the accuracy of my predictions. So what is aeroelasticity? It's also referred to as fluid structure interaction, and it represents the interaction between inertia, elastic, and aerodynamic forces. So you can see that this represent aeroelastic equations of motion. And you can see on the left-hand side is just a damped harmonic motion, and on the right-hand side is a forcing term, which comes from aerodynamics. So as you can see from the nature of this equation I've written, that the aerodynamic forcing is a function of x, the displacement, and x dot, the velocity of the displacement, and time. So this equation is highly nonlinear. The other way to describe aeroelasticity is how does a solid body react to fluid forces acting on it, this term, and how does the fluid flow change in response? How does this, when you change the x here, how does the fluid forces change? I'll try to show you an aeroelastic event here. This is representing what you can think of it as a wing in free stream. And stream. So we have a wing sitting in a free stream, and we start blowing air over it. And as the air starts flowing, you can see initially it displays to a new position and then starts vibrating. As you can see, and the vibration repeat themselves and go to a limit cycle. So this is a natural way that aeroelastic event would happen. And I would describe in a later part of this presentation that how does this flutter occur in this case. And I have to say that most of the cases which involve aeroelasticity, you usually converge to a limit cycle. So the amplitude of the vibration is limited. And consequently, most aeroelastic vibration results in high cycle fatigue, i.e. you do not break something immediately. It starts developing cracks during the period of using that component, whether it's a wing or a component of the turbomachinery. So the engineering components which are affected by aeroelasticity are, actually I showed the aircraft wing in the previous slide. So wind turbine blades can flutter and have other form of aeroelastic instability, bridges, skyscrapers, oil platform, and most components of aero engines. This is which is the focus of my presentation today. In fact, just as a matter of interest, if you are interested to know, also the snoring is also an aeroelastic instability of human soft palate at the back of your throat. So you start fluttering it, and hence it produces that noise during the night when you sleep. So, but aeroelastic events on aero engines can be fatal and can be quite devastating. So therefore, most engine manufacturers spend a lot of time to make sure that do not have aeroelastic failures. So an example of this failure is this Midland aircraft, which crashed in 1989, somewhere in Midlands in UK. And after investigation, they found out that the cause of this crash was the flutter of one of the engines, which consequently resulted in the aircraft crashing. The other aeroelastic event that people usually do not appreciate comes during the foreign object or bird strike. So usually the bird strike itself, given that if the bird is not very big and the blade is designed well, does not result in failure of engine. So a bird strike would create just a dent, as you can see here, on the fan blade. However, consequently, motion that results in a scenario like this, and then a scenario like that come from the aeroelastic event, which I will hope to cover in the next presentation. So bird strike failure due to small birds is usually due to aeroelastic failure. In fact, as because we are moving to more radical engines, we're trying to reduce weight, we are trying to optimize the fan blade for or any component of turbomachinery for performance. The vibration events are becoming more and more. In fact, the vice president of technology and uh, environment at Pratt and Whitney, Alan Epstein said that our aero engines are in the process of shaking themselves to death. So consequently, aeroelasticity is becoming more of a relevant issue. It has always been relevant, but with the new design, as I would try to explain it later, becoming even more of a issue for engine designers. So just going to just giving you an idea before going to the theory. If you look at this crash, I mean, obviously, what caused it is I try to demonstrate it here. Sorry, I need to change my pens before I can present the videos. And here,
is for high-speed motion picture cameras. The shaft of the test propeller.
You can see that you start revving a fan blade. This is representative of a fan blade. And through some elastic bands is connected to a shaft, to a component at the back, which can be representative of the LP turbine, which turns the fan blade. You can see as the loading on the blade increases, the fan blade starts shaking around. And this is completely obvious. So you can see that if such event, and you can see this motion becomes more and more, and that was the cause of the failure here on this engine, where the vibration of the fan blade caused by the aerodynamic on the fan blade couples by the motion of the LP shaft, LP turbine through the low pressure shaft, which turns the fan blade and cause this catastrophic scenario. So now I'm going to try to explain the basic principles of aeroelasticity in terms of 2D aerofoils, which are going to be representative of a cross-section of any one of the components of the turbomachinery. So obviously, because they are all working on air, I'm just looking at the fan blade here. Let's just assume that we are looking at the fan blade. Obviously, fan blade is a lifting device, so there's going to be lift forces on it. So we model the aerodynamic in terms of a 2D flow past an aerofoil. And also we look at the structural mechanic of the system in terms of a 2 degree of freedom, plunging and pitching. So the 2 degrees of freedom here is plunging displacement, a plunging displacement here in terms of in the edge, and also a pitching or a twisting in terms of alpha. And it is modeled by assigning a spring plunging stiffness and pitching stiffness and with the corresponding dampers. So this is the model I'm going to try to use to explain the basic aeroelastic phenomena. So first of all, before you start doing any dynamic aeroelasticity and looking at the dynamics, you need to look at the steady aeroelasticity. Obviously, any component in turbomachine or wind is a lifting device. So consequently, it would have a lift and also a moment. So consequently, the shape that you design, the shape during idle operation, stationary, is different to the shape during the operating condition because it has lift forces and also moment acting on it. So consequently, it changes the shape of the aerofoil. The moment is especially important because you can imagine that when you have a moment, it tries to twist the blade more open. Consequently, the angle of attack to the blade increases. So it's very important initially to be able to model static aeroelasticity. So just looking at it in terms of 1 degree of freedom plunging here. So we have airflow, it creates a lift on the blade, and the lift forces are going to fight against the elastic forces by damper and stiffness and try to displace the blade. And you can, for a plunging motion, the lift is to the first order approximation. It's just function of, it's not function of time, it's just a function of velocity. And consequently, you can find the shape of deformed shape of this aerofoil using this simple equation, and you can compute the displacement in terms of L over K, which gives you the new position of the aerofoil. Obviously, this is under assumption that the lift is much higher than the gravitational forces. The other thing that you should notice, which usually results in sudden breaking of something, is for L large enough or K small enough, the aerofoil will experience divergence and it just doesn't go to another place. So this is quite important, even though it doesn't change the geometry a lot. You can see that by displacing the aerofoil, you are going to have some steady forcing in the spring. So even though there's no vibration, the steady loading of the blade has already created some forces on in the spring. So that's one of the things which happens. Obviously, when you go for a twisting motion, as you blow the air, you create a moment. This is a 1 degree of freedom twisting motion, which is characterized by a twisting degree of stiffness. And you can see it here, as the air blows, you create a moment, and the moment try to twist the blade or the aerofoil further. So here, the equation is a bit more complicated as it becomes nonlinear. And it's also very important. This is one of the most important things as I will show later on in my fan section. This is one of the important parts for designing the fan blade, because what happens, you're going to change the stagger of the blade. Consequently, you're going to change the angle of attack or incidence to the blade. And you could, even though you've designed it during the idle condition, it's got the proper angle of attack. By putting the extra moment and twisting further, you can move the flow towards stall. So that was regarding the steady loading. So there are different types of unsteady aeroelasticity. And if you look at textbook, you see different names and different authors and different countries use different names. And here I try to summarize different types of aeroelasticity that I'm aware of. And the fact that different types of aeroelasticity are classified is according to how the unsteady forcing on the blade is created. Different format, different way that you create this unsteady forcing in literature, you find different names. So for example, Flutter, which is the main topic of this presentation, the only source of unsteadiness comes from the blade vibration itself, i.e. the fluid dynamics can be completely steady. So if the blade is not vibrating, the aerodynamic can be fully steady. The only form of unsteadiness comes from the vibration of the blade. There are other forms of unsteadiness, unsteady aeroelasticity. For example, buffeting is caused due to the unsteadiness in the flow. This is a bit different to here, because here the blade vibration is the only source of unsteadiness, where in buffeting, Flow and the unsteadiness is already present in the flow. So the unsteadiness comes from the aerodynamics, such as vortex shedding or shock movement. The other term that you hear in aeroelasticity quite often is called force response. And this is from other components of turbomachine or upstream or downstream flow asymmetry. For example, as the rotor goes past the stator, it would see a stator as a blockage. Consequently, the flow on the rotor changes, creates unsteady forcing, and hence the term force response. And finally, the other way you get aeroelastic response is due to acoustic resonance. And it can be initiated by any of these above, but then is amplified due to acoustics, such as the acoustic of the intake duct or plenum. And for Flutter, today I will show that this acoustic resonance in the intake duct is quite an important parameter in fan flutter. Flutter. So what do I mean by Flutter? What is Flutter? I mean, in terms of word from the textbooks again, Flutter is instability of an elastic structure in a fluid flow caused by positive feedback between the body's deflection and the resulting forcing exerted by the fluid flow. So what does it mean? I mean, in terms of trying to explain it. So you got a structure, which is this structure now is sitting at its equilibrium. So it has already deformed due to static loads. So you give it the slightest displacement. So when you slightly displace the blade, the vibration creates unsteady forces on the blade. So there could be two scenarios. In the first scenario, the vibration is out of phase with the forcing. So you can see that as the vibration wants to increase, the forces on the blade increase. So consequently reduce the displacement. And this works like a damping. This is a stable case and works as a damping. And this is known as aerodynamic damping. So consequently, because they're out of the phase, the vibration decreases, aerodynamic forces decreases, consequently vibration decrease, and so it's a stable system. And this is a typical behavior of a stable scenario where there is no flutter. You give it a displacement, as in time, the deflection, the vibration dies. Just for your information, the rest of the presentation, I will refer to stable cases as cases with positive damping. However, there's another scenario that what happens is you give it a slight displacement, the vibration increases, then you create the unsteady forcing is in phase with the motion of the blade. So consequently, it increases the vibration of the blade. So consequently, the vibration increases. So it becomes a self-feeding loop and the case becomes unstable. This is what we call flutter. And in this presentation, I refer to it as negative damping. Obviously, usually all flutter cases do not grow indefinitely and usually reach a limit cycle due to a non-linearity of the system. So this is a unstable, stable case, as is quite obvious from this picture. And again, I emphasize for flutter, blade motion is the only source of unsteadiness. You can have the best aerodynamic, but if you manage to create a motion which is create a forcing on the blade, which is in phase with the motion of the blade, then the displacements are going to grow. I try to give an example of this, but this is, you have to take this with a pinch of salt because it is how, so let's go to this one first. So 1 degree of plunging aeroelasticity model. So we have a constant model. We have a flow past the aerofoil at velocity u. The aerofoil already has deformed to its deformed shape due to the steady loading. And so we excite the system with a small displacement x. And consequently, we create an extra lift on the blade, dl. dl here is going to be a function of x dot, which is the velocity of the blade, because if you look at the velocity triangle, you can see that the effective angle of attack now changes due to the motion. So this is u, which gives you the original angle of attack. This is velocity of the blade. Say, imagine it's going down x dot. This gives you another velocity. So the relative velocity of the blade, or the effective angle of the attack that the blade now sees, is this. So the lift becomes a function of angle of attack to the blade, which is a function of velocity of the blade for the plunging motion, obviously. And so the equation of motion for this 1 degree of freedom system become of this form, where dl is a function of x dot and t. And you can, easy manipulation, you can show that the blade will flutter if the unsteady lift, delta L, becomes in phase with the velocity of the blade x dot. In fact, this is very important to recognize that flutter occurs when the unsteady forcing is in phase with the velocity of the blade, i.e. the blade motion, not the displacement. You can easily work. If the force is in phase with the displacement, you would not get any damping, whether positive or negative. So under what scenarios could you get such a situation that the blade lift you create becomes in phase with the velocity of the blade? So this is the case I was talking. You need to take this with a pinch of salt, because this is not really representative of reality, but I'll just try to demonstrate how can the blade become the velocity and lift can become in phase. So I've used a quasi-steady demonstration of flutter for 1 degree of freedom aerofoil in plunging motion. So we have a aerofoil here, which is plunging up and down. And you can see this is the relative angle of attack it sees as it's going up and down, as I showed you before. So without going too much in detail, I mean, if you can try to work it out later. So when it's, this is lift against angle of attack or incidence, you can see, again, I'm saying that very important assumption that flow remains steady on the negative part of the lift curve, i.e. we assume the flow is steady, which is a big assumption, which is not true. So, but just for demonstration purposes, you can see that as you go from, this is T1, T2, T3. So as the blade moves, so it's T no, T1 equal to no, T2 is here, and then it comes back to the original place. Yeah. So you can see that as the blade moves up, you can see that it goes to a higher angle of attack. So consequently, the lift created on the blade increases, which try to move the blade down. And you can see while you are in the proper part of the incidence versus lift curve, i.e. unstalled part, the lift that you create, the shown by this curve, is always against the displacement of the motion of the blade. So you are always out of phase. So that during this scenario, you're always damped. However, you can see this opposite case happens due to lift decreasing as angle of attack increases in the stalled part, and the lift becomes in phase with the motion of the blade. So in this case, the flow can become unstable. Obviously, as I said, this is just for demonstration purposes. Another way that the components flutter is during the modal coupling. If we have played this video that played earlier on, and if you notice, first thing which happens, if you look at this video, this has already described a couple of things that I have described before. So if you notice what happens, initially, while the flow of the air is not in the flutter regime, the only thing that you do is move the blade to a new static position. So this is the new position of the blade. So this is a static deformation. And then consequently, what happens, it starts vibrating about this new static deformed position. And if you stop, let me try to hopefully stop it at the correct time. No, you can see that the blade is not vibrating in a plunging or a pitching motion. What is vibrating is a combination of plunging and pitching. So you have created the mode that plunges and pitches. And this sort of scenario is quite common for wings when they flutter, is if you take a 2 degree of the freedom, where h is the plunge degree of freedom and alpha is the pitch degree of freedom, what happens? Instability occurs when lift and or moment couple pitching and plunging motions. So consequently, the aerodynamic forces manage to couple the two modes, plunging and pitching, and they react as one mode. And consequently, during these scenarios, the thing which happens, the lift that you create due to you create a lift due to the plunging motion as the blade goes up and down. But as you saw before, for an unstalled blade, this is always against the motion. But what happens in such scenario, the pitching motion also gives you an extra lift, and that extra lift becomes in phase with the plunging motion and causes the blade to flutter. So that was some basic theory of static aeroelasticity, as well as how blades flutter. Now in this part, I'm going to look at it says aeroelastic issues for fan blades, but in this presentation, I've said before, I'm just going to concentrate on flutter. And obviously flutter fan blade is a real important component of modern aero engines, and it creates about 80% of the thrust. And as we are moving to higher bypass ratio engines, this ratio is going to get bigger. In fact, just this is independent, irrelevant to the rest of presentation. Fan blades are really important, that no matter how we're going to turn it when we go to future aviation, with our current design, we are always going to have a fan here. Whether it's been turned by electricity or any other means, we always going to have a fan blade. So fan is really important part of the aero engine. And I'm going to today try to talk about is flutter. And just before we go, flutter is not only for the fan blades, but it can happen to the core compressors, turbines, and also the seals, which sit between the rotor and stators. So how do we solve this equation? This equation is highly nonlinear, as I said before. And if you try to, and this side of equation by itself requires very big unsteady Urans CFD computations at the very least. So you cannot really, and if you think of it, this term on the left-hand side usually is done in an FE using finite element method. So to do it fully coupled and try to solve them together, you need to couple a finite element code and a CFD code. And due to different time steps and other restrictions, this is not really feasible at the moment. So you have to either try to simplify where you calculate a F or simplify the FE part. The good thing about the turbomachinery blades is they have very high mass ratio, i.e. the mass of structure is much bigger than the mass of the fluid. So consequently, the vibration characteristics do not change due to the aerodynamic forces. It's not like the previous video that I showed, like for that wing, that the air managed to couple the flap and the torsional mode and create another mode. And the structure remains linear, i.e. the structure can become non-linear, but by the time the structure becomes non-linear, you are not really interested. So these are the good things about components of turbomachinery. So the way then we solve them, we use something which is called partially coupled. So before we start our CFD, big unsteady CFD Urans computation, what we do, we calculate the mechanical properties of the blade, such as damping and structural mode shape. And then we map those to the CFD grid. So we map these mode shapes to our 3D CFD grid. And after that, we do not look at them anymore. And we write the displacement of the blade as a summation of frequency of the blade times the shape of the mode. These are the mode shapes of the blade for a typical fan blade. So these are the contours of displacement plotted here. So this is the first flap mode, which is typical of fan blade, which is a mixture of a plunging and a twisting mode. This is a second flap mode, first torsion, and first edgewise. So we usually interested in basic modes like that. And then we interpolate this displacement from the FE onto the CFD grid, and we never go back to the FE again. And we solve this system starting from a given time step. We solve for unsteady pressure P using our URANS, which in this case is a compressible flow solver. Then we use this unsteady pressure to solve for the modal displacement, these modes. And then we sum this modal displacement and we get a total displacement. According to this displacement, we deform our mesh, and then we move to the next time step and we compute another CFD URANS computation. And this is the way we do our computation. And in a way, if you think of it, it's called uncoupled, in a way that the structure motion is slightly lagging the fluid motion. But due to the frequencies we have for for gas turbine, turbomachinery component, this assumption has not proved to be too bad. So, I mean, just to give you an example, this is how the mode shape works. This is an example of a cantilever beam, and you can write the total displacement as the sum of fundamental modes, which is the first flap, first mode, second, third, and this is exactly here. We write the displacement of the fan blade as a sum of these displacement for different modes. So, okay, again, to start with, before we start any Flutter computation, we have to get the running shape of the blade. So we need to solve a system like that. So we have the center of twist of the blade, which comes from the summation of the displacement of different modes. Here we have 5 modes. And what happens is that we have the centrifugal forces and aerodynamic forces which try to untwist the blade, and we have restoring torsional stiffness which try to bring back the blade, and consequently we change the stagger of the blade and we get a shape which is called the untwisted shape of the blade. So first of all, we get the running shape of the blade, and this is really important because the running shape of the blade, or untwist, which is known in turbomachinery, is particularly important for high aspect ratio blades such as fan blades, as the running shape, stagger of the blade, determines the tip clearance, the distance between the rotor tip and the casing, the performance. So this is a bit exaggerated. This is a plot of mass flow against pressure ratio for a fan. And the black line has obtained with a black blade and the red line with a red blade. And you can see that the performance of the blade changes quite a lot if you use in your CFD computation the running geometry or the idle geometry, the efficiency, stall boundary, flutter boundary, and also the noise. So first thing you calculate the running shape of the blade. So now, finally, I've come for the last 15 minutes. I'm going to try to describe Partspeed stall flutter, which is one of the common forms of flutter on fan blades. And I'll just say, because even though it's called stall flutter, you do not require any stalling of the blades before for this event to happen. So let's describe what do I mean by Partspeed stall flutter. I'm not sure, I think you would all be familiar with a fan map, which is here we have mass flow rate in the x-axis plotted against the pressure ratio. This is a common fan map, or if you think of it in terms of aerofoil, that's the negative angle of attack against lift of the blade. So this is a typical fan map or a compressor map. And here you got speed, different speed. So you got 100% speed, rotation speed of the fan, 80%, 60%. And you can see, obviously, as you increase the rotation speed, the sucking power of the fan it gets more. So both pressure ratio and the mass flow goes down. So taking it, for example, that I'm a fan blade designer, first thing is I come and I put the constant speed characteristic at some running condition. For example, this is sort of landing, this is sort of takeoff, near taxiing, and this is cruise. And on top of that, determine a working line. So if everything goes well, as you accelerate the fan blade, you just go up this working line. And this is determined by geometry downstream of the blade. And then you do a calculation and you get the stall line. And the distance between the working line and the stall line determines the safe operating condition of the fan. So this is represent the safe operation of the fan, the distance between the working line and the stall line. And as an example here, you think this is quite a good blade of design. I've got my working line here and I've got my stall line, and there's a big distance. So I'm very far from any instabilities. Then you put this rig or this and you put it inside the test, and you notice that in some certain speed, you do not reach the stall boundary because the vibration becomes very high and you have to stop the testing and you get flutter. And as you notice, you have taken a sort of like a bite out of the stability range of the blade, and consequently, this is called a flutter bite. And you can see that now, for say 80% speed, the flutter bite has come very close to the working line. So you have lost a sufficient amount of stability from your fan. And consequently, that's the reason that flutter is becoming a very important issue for engine designer, fan designer especially, because in a lot of speed, you would not reach the stall boundary. Your blade starts fluttering before you reach the stall boundary. Consequently, you lose a lot of stability margin. So whether you stall or flutter, it's not very important. The engine becomes unsafe. So then the stall boundary becomes very close to stall boundary. Some might say that you're still not on the working line, but however, you want quite a big margin here, because what happens is initially when you have your fan blade, you got a nice leading edge shape. Forgot to, sorry, my pointer was not pointing. So I'll try to, so again, these are the constant speed characteristics. So there's a fan performance at different speeds, and you get this working line, and then you put the stall line here, and when you get flutter, you can see that you lose a chunk of your stability margin, and it looks as if you've taken a bite out of the stability margin, hence the term flutter bite. And you can see in such scenario, the flutter boundary becomes very close to the working line. So that potentially could be dangerous, because when you initially get your blades brand new, they have nice leading edge shapes like the red one I've shown here. However, as the blade becomes older due to natural wear and tear, foreign body object damage, and so on, you start losing leading edge. And consequently, in a one way you can think of losing leading edge is you are moving your working line to a higher working line, and consequently you could reach potentially a situation that your working line goes through the flutter bite and it becomes unstable. So consequently, you want to have a large margin between your flutter or the most instability and your working line. So what causes the elements of stall flutter? And this is the area that of research for many years, and more or less we understand some parts of it, but there's still a lot of unexplored areas in it. So our work has shown that elements of fan stall flutter, which gives you this flutter bite, are first of all the nature of flow on the suction side of the blade. So this is the suction side of the blade. The flow is coming from right to left from this direction. And what happens is at certain condition, you start getting radial migration of the flow up the blade. This is one of the elements of stall flutter. This is not unsteady. This is just a radial migration of a sort of a 3D separation, but the blade is still working on stall with positive pressure ratio. The other element of Flutter is the shape of the first flap mode shape. And if you notice, oh, here, sorry, the leading edge is in the, this is leading edge, this is trailing edge. We have a blade. It's not pure flapping. It's a pure flapping mixed with a bit of twisting. As you can see, these are the contours of the displacement, and the redder it is, the higher the displacement. And you can see you got higher displacement at the leading edge than the trailing edge. This is the second element for a stall flutter. And the other parameter, which is very important, and we found out, is the acoustic of the intake. And this happens due to the fact that the vibration creates a pressure perturbation, which travels down the intake duct. When it reaches the highlight, as you're changing the impedance, some part of it go out and some part of it reflect and go back towards the blade. So the phase that this reflected wave comes to the fan can affect the flutter of the blade. So I try to go through this rest of this thing in the next 10 minutes. So just to give you an idea, how does a flow, for the people who are not familiar, how does the flow in a fan blade looks like? So this is your typical fan blade. And if you cut a cross section at about 90%, this is a straight line, but it's not really straight. Cut a cross section at 90% height from the tip, and you look at the Mach number contours, you can see that in most of the cases we are solving, the flow is transonic, and it's got quite a strong shock, which is outside the passage. So this is the typical flow for a Partspeed blade with a strong shock sitting outside the passage. So just to give you an idea. And what else happens? So again, looking at mass flow pressure ratio on the working line, obviously the blade has been designed to work on the working line. You can see that if you look at the streamlines on the blade, they nicely follow the streamline section and they behave nicely, as which are this point. At this point, they behave like that. And if you go towards the flutter point, this is the stall line. So you can see it's not stalled. You start getting some sort of radial migration. And let's forget in that. Now, if you now look at, again, this is the same plot. Here we got mass flow against pressure ratio. And on the right plot, I have plotted mass flow against damping. So this is as you throttle up the working line, you can see that this is damping. As I mentioned before, negative damping means unstable. As you start throttling the blade starts losing damping, and it reaches the point that it suddenly drops to the negative area and becomes unstable. So how does this happen? If we now plot, this is, I'll try to explain this. If you plot the component of damping, so if you decompose this damping at different radial sections, and plot it. So here I've plotted damping against radial sections. So for example, if you take the black curve here, and if you sum up all the points on this black line, you would end up getting this damping value. And if you add up all the points on the red line, you get this damping value. So you're looking at how different section of the fan blade behave as you go up the working line. You can see that they behave quite similarly and they're all stable. And the area that is mostly affected is the area upward of the flow migration, where the aerodynamic damping in this region becomes negative and the blade becomes unstable. So most of the instability for the most of the fan blades that I've looked at happen upward of the migration area. So, but the problem is when people want to design it, the people design this area. But if you notice, the problem comes from further down. And if you want to redesign the blade, you really ought to redesign further down the blade rather than up here, because the mess up here is caused by what's happened down here. The other element of the flutter that I said is the shape of the 1F mode. So this is the 1F mode. Those are contours of displacement. And you can decompose this mode to a pure plunging component like here. So you take all the displacement at the radial height, add them together and average them, you get this. and then you subtract this from that, and you get this component. So you can see that this 1F mode shape, the first flap mode shape, can be written as a plunging mode shape component plus the twisting. And our work has shown that the more the amount of twisting increases, the flutter instability becomes worse. In fact, if you have sufficient amount of twisting in the mode, you can make the blade flutter even on the working line when the flow is completely nice. I mean, if you have a completely nice flow even on the blade, if you have sufficient amount of twisting in the 1F mode shape, you can make it flutter. So this is but this is going to take a while before trying to explain this. But the interaction between the mode shape and the flow on the blade is highly nonlinear. So, for example, here I put alpha, which is the mode shape, and the bigger alpha, the bigger amount of twisting it has in it against damping for different flow condition, and 1 is your working line. And you can see that as you for a blade which has got pure twisting, pure plunging, i.e. just doing a bending motion, the aerodynamic damping is quite independent of the mode shape. So you can see that, of the flow on the blade, so they have the same damping. But this situation has become very nonlinear, or alternatively, if you got a very nice flow, no matter what you do to the mode shape, the aerodynamic damping doesn't change. So this problem is very nonlinear, and I've tried to understand this for many years, and I have not been that successful. So consequently, recently we have used to move to machine learning models for this to try to understand it. So finally, I've got a few minutes, acoustic of the intake. How does the acoustic of the intake work? Because that's really important. That is what determines your flutter speed. So just try to give you some, so usually when the blades flutter, they do not flutter in phase. So this is the contours of displacement, instantaneous contours of displacement for the first flap mode. And usually the blades flutter with a phase difference between different blades. So you can see that here, the blades here, top here, are got positive displacement, i.e. coming out of the page, and blades here got negative displacement going in the page. And here you can see two lines where there's no displacement, and it's called nodal diameter. So here you see two lines with displacement 0. So this mode shape is called two nodal diameter. This mode shape creates a spiral wave. Now, if you look at the instantaneous unsteady pressure in the duct at 90% height, so we cut around the duct at the 90% height, and we're looking at unsteady pressure that you're creating. So you can see this represent that, and this represent that. So the vibration creates a spiral wave which goes down the duct. And the acoustic of a spiral wave are quite difficult. I mean, they are not as simple as a plane wave, because a plane wave, unless your flow Mach number becomes bigger than 1, it always propagates. But for a spiral wave, you need to take into account the direction of the wave and so on. So these waves now propagate down the intake duct. And what happens? They go down until they reach the highlight. And when they reach the highlight, part of the acoustic wave, as I said before, it goes outside the duct, and part of it reflects back to the blade. And obviously, the phase that this downstream pressure comes back to the blade determines the stability of the blade. So if the unsteady pressure, this reflected wave comes to the blade out of phase with the motion of the blade, you can see that is going to have damping effects. And if it comes in phase, obviously it's going to increase the vibration and the blade becomes more unstable. So consequently, this is a very important parameter for flutter, the intake. And the length of the intake and the Mach number of the intake determines the speed where flutter could occur. There's also downstream reflection between the fan and the OGV, but the OGVs here have been designed to straighten the flow. So the reflection coefficient is very small there. So flutter bite is introduced by influenced by interaction of fan blade with upstream and downstream acoustic waves. So this is very important. So proper modeling of fan, I had spelled it before wrong. This is not flutter, it's flutter, requires modeling of intake. So just quickly, how good is CFD? So we just go listen, look at this curve, forget the writing. So we got two speed lines. This is a real test case. And the black lines are the CFD speed lines, and the brown are the measure speed line. And the red line is the stability boundary using this long intake. And you can see that this is the measured data. It did not flutter at all. So the blade was stable from a flutter point of view at all the speed. And all the unstable points here refer to stall line. So the blade only stalls. So you can push it as far as you can. Then the same fan set was replaced, was put in a short intake, which is a representative of a flight intake. And you can see this is the measured data that it produced. So you can see that at higher speed and the lower speed is still stalled, but at this certain speed range, you can see that he has produced a big flutter bite and he has brought it towards a high working line. And looking at CFD, you can see that CFD has had a good prediction of the flutter boundary as well. The reason is, before going too much in detail, that a lot of acoustic effect of the intake are potential effect and come from acoustic. And we know CFD is good predicting acoustic and Euler problem. It's not as good doing the Navier-Stokes and the stalling problem. So consequently, it usually does a good job getting the flutter boundary. So, so what are the current prediction methods? Current prediction method for Flutter, you can spend millions of quid or euro and make a test rig and try to do experiment and hope that you get some result, but it's not guaranteed. Or you can use high fidelity CFD and try to model your cases using CFD, which is much cheaper. Obviously, I'm a CFD believer. I'm not a CFD skeptic. And I think this is quite a good representation of the CFD results. However, sometimes when you talk to CFD skeptics, this is, I promise I'll finish in 3 minutes. I hope I haven't bored you too much. This is the CFD measure flutter boundary for a fan blade. And this is the measure flutter boundary. And when you talk to CFD skeptics, and they tell you that there's a difference between CFD and measure data. But one thing you have to realize that CFD works in a perfect world, i.e. assumes all the blades are the same, all the blades have the same stagger around the annulus, and all the blades have got the same frequency. However, when you do a measurement of the blade's frequency, this is blade number, this is a 20-bladed disc, and mistuning means the variation of the frequency from the design frequency. And you can see for a certain pattern, you can get high variation in mistuning, i.e. different blades have got different frequency. And it's well known that mistuning has got beneficial effects on damping. So consequently, if you add the correct amount of mistuning in your CFD results, and you can see that your flutter boundary goes very close to the measure flutter boundary. So not all the problems always come from CFD. And let's forget that. And thank you. And just giving some concluding remarks that fan blades in the modern high bypass air engine typically produce around 80% of the thrust. And to achieve significant improvements in fuel efficiency, new design concepts are required. An example such a design is Rolls-Royce turbofan ultrafan, which is shown here. And this is a very high bypass ratio, and consequently, in order to reduce, and so the blades are much longer. So in order to reduce the weight of the blades, they have to be designed by composite. So you become, and also to reduce the overall drag and the weight of the propulsion system, i.e. aircraft from the engine, with the engine, you use shorter intake. And these are lower speed fan blades, so they become by nature more loaded with higher diameters loading slowly. So you can see, if you look at now the equations of elastic equation, what's happening? We are reducing the left-hand side, we are increasing the right-hand side. So the aerodynamic loading becomes bigger, and when we are reducing the stiffness and masses, and so consequently you expect the aerodynamic aeroelastic event become worse. So this just looking at that equation and new design, you expect more problems. Also, the shorter intake, without going too much in detail in it, means that your flutter speed moves to a higher speed, and consequently it can be in your design speed. So accurate and fast prediction are needed during their design. And the other thing is aeroelastic engine rig tests are very expensive, especially in case of failure. So if you do a design of an rig and you put it and it fails, then you're going to lose a lot of money without not much getting data. And consequently, with the increasing power in computing, a lot of researchers are now moving to CFD-based model. And it's envisaged that research in computational aeroelasticity will increase. And just to finish, aeroelasticity, you have to remember, is a multidisciplinary subject. When I started many years ago, I thought if you know CFD, you can do aeroelasticity. But I don't think it's correct. You need to know about CFD, aerodynamics, structural mechanics, acoustic, and how different things couple. And I'll finish on this, that we are moving to new engine architecture. Whatever way we do, still all of these designs seem to have a fan blade, and we don't know how they're going to behave in aeroelastic terms. And we cannot do rig design for every one of them and try to look at the concept. So we have to remember, so computational elasticity is going to become much more important. Thanks very much for listening for over 1 hour, and hopefully I didn't bore you too much. Cheers.
Okay, thank you very much for this very interesting talk with very complex phenomena. So I think it was very well for some people like me. And so now we can have some question. So you can just unmute your mic and go ahead actually. The other possibility is to write on the chat and I will read the question, but
I cannot see the chat because I've got my screen as
yeah, but I will do it actually if so please go ahead.
Yeah, I may have a question.
Yeah, sure. Please go on.
Yes.
First, thank you very much for this very nice and pedagogical presentation. I am a pure aerodynamic guy, and I have the feeling at the end of the presentation to have understood a lot of concepts, and so thanks a lot. Maybe one short question. Many of your explanation, especially in the first part of the presentation, were linked to an isolated blade, and in a turbomachinery and in a fan, you have several blades. So what is the importance of the interaction between the blades for such kind of phenomena?
Well, that's a very relevant question, because as you said, if you look at this plot, you have a passage. And from my experience, the things become important when you start having vibration, you change the shape of the passage. So you can see, because as I told you, the blades do not vibrate in phase, they vibrate out of phase. So consequently, you could be closing the nozzle or opening the nozzle. So that plays quite an important part in Flutter. The other thing which I found is quite important is the area of the covered passage, i.e. the area which sits between two blades, which metal is on the top and metal on the bottom. So these two are quite important because they determine the shape of the passage as the blade vibrates. is quite important. The other thing that becomes quite important is because the blades, again, these are all important because the blades do not vibrate in phase. They all vibrate out of phase. So this blade doing something, the incidence that it creates on the trailing blade could change. So all the blades at a given time do not see the same incidence due to the vibration, because not only due to the motion of the blade itself, because it's going to be different, but also the vibration of this blade would feed into its trailing blade. So from an aerodynamic point of view or acoustic point of view, is much more difficult than the single isolated aerofoil like wings. But the advantage they have, the easier part of it is that the mechanical mode shape are, because the blades are heavier than wings, the aerodynamics doesn't change the nature of vibration too much. But from the aerodynamics, they are a fair bit more difficult. And the other thing that I didn't at all mention is the leakage flow. I ignored it through this presentation because the flow coming from the pressure side to suction side would influence the flow on the upper part of the blade, which consequently can feed into the flutter part.
Thank you.
Did I answer the correct question?
Yeah, thank you. Thank you very much. May I ask an additional question linked to the answer from? So does it mean that you always need to do full annulus CFD simulation? You are not able to predict correctly Flutter by doing a simulation on a single blade channel?
Yeah, we do that because what we do, we put a phase lag boundary condition. So on the top and the bottom, they are at different and so we use phase lag boundary condition, and you can just do one passage. But when you do one passage, you can do one interblade phase lag or nodal diameter at each go. Moreover, another thing that I found from my experience, I mean, I've always worked on non-linear, linear CFD code with proper phase lag boundary condition between the two blades would give very similar results. If you feed it the same steady CFD solution to a linear time domain computation and to a non-linear time domain computation and a linear frequency domain, the results are very similar because the vibration amplitudes usually are quite small.
Okay, thank you.
So
thank you very much.
Expose the periodicity through phase lag boundary condition at the periodic boundary.
Okay, there are some other question. Please feel free to unmute your mic.
Somebody has raised their hand.
Yes, Candero, Kato.
Yes, thank you for your presentation. Yeah. I have a question on your explanation in slide 27.
Yeah.
So previously, yes. And you said the messy area outside is caused by the something inner part. And you mean the disturbance or inner radial location is propagated to the outer location?
So this is the fan blade. I don't know whether you could see my, because I can, this is my fan blade, yeah? This is the spinner, and this is the intake cowling, yeah? That's the intake. Okay, so if you think of it, let's ignore the spinner. So the spinner changes the acoustic nature. You get some reflection at a point that the spinner finishes, but we can ignore that for the time being. When you got blade vibration, you create a pressure wave. And this pressure wave, because as I showed you, because it vibrates in a nodal diameter pattern, it's not a pure plane wave. It's got an angle. It's a spiral wave. This wave propagates through the intake duct till it reaches the highlight. And at the highlight, you are changing the impedance of the acoustic wave. So consequently, as soon as you change the impedance of an acoustic wave, you reflect some of it downwards to get a reflection. So this wave hits the intake highlight. There is no, this line is just trying to show the intake highlight, but some of it goes through, comes to the outside the engine, but the part which reflects, which goes back is the important part. So,
Okay.
yeah. So, I mean, let's think of it in terms of noise. I mean, if noise people, if you are interested in community noise, and we could get all the acoustic mode due to the blade rotation reflected at the highlight, we would have been really good because we would have not heard the fan noise. Unfortunately, the waves due to the fan rotation is cut on and it will propagate outside. So it's like a flutter noise which reflects at the highlight and some of it goes back. So this happens for most of the other components of turbomachinery, like the compressor blades. This is really important because when the compressor blade, like your rotor, starts vibrating, especially at part speed, when you close, you have your VSVs at the closed condition, a lot of that pressure wave you create due to the vibration of the rotor would reflect from the upstream stator vane and come back towards your rotor. And that would determine the flutter stability of the compressor.
Okay, I see.
Yeah, so a lot of compressor flutters are related, especially at lower speeds where you have closed your stator vanes, yeah, and your variable stator vanes, which comes from the vibration caused by the rotor hitting the upstream and downstream stator vanes and reflecting.
I see. So there's a kind of like a feedback system.
That's right, yeah.
Okay, it was very nice to learn. Thank you so much.
Yeah, I mean, this, and another thing here, you are sort of creating an acoustic resonance in a way as well, because the pressure wave, I don't know whether you are familiar with cut on and cut off acoustic waves. Cut on means they propagate, cut off means they don't propagate. Due to the turning, the acoustic wave downstream of the rotor is cut off, i.e. it's not propagating. So you got a cut off acoustic wave here, and you also have this reflection. So it sort of works in terms of like a resonance in there.
I see. Thank you so much.
Thank you.
Some other question?
Jean-Philippe, there is a question on the chat.
Yeah, there is a question on the chat. So I will read the question. Maybe the speaker cannot ask himself. So you mentioned computational aeroelasticity will gain more importance. What type of upcoming method tools do you think will be needed to improve simulation and understanding? You already alluded the machine learning. Would you comment on the need of high fidelity and large scale simulations?
I think for Flutter, personally, this is a personal viewpoint. For Flutter, if you can get your base mean flow correctly, then you can use any linear code to predict your Flutter. I think we get very similar result. The whole idea is how are we going to get the steady mean flow correct? And that comes to turbulence modeling or using high fidelity CFD, whether we can run high fidelity CFD to get your mean flow. I think that from my personal experience that the hardest part of getting Flutter correctly is to get your mean flow correctly. And the reason that we results I show here are quite decent is over the years, while I was working with AU3D, we have tuned all the parameters in the turbulence model to be able to predict good mean flow for the fan blades that we are working on. So with number one importance, in my opinion, is getting the mean flow turbulent flow correctly, and is getting somehow turbulence going correctly. Obviously, there are problems that I haven't addressed here, like what they call NSV, non-synchronous vibration, due to some form of stall at the tip or tip instability. Those problems then become non-linear, and you need to model it high fidelity, both in terms of steady and unsteady. But for Flutter of this type, I believe that if you can get a mean flow, your linear solver should be sufficiently good enough.
Okay, he seems to be happy with the reply actually. So, is there some other question? Yes. Yes, go ahead.
This is Rocky. I mean, hi, Mehdi, how are you doing?
Rocky, what you doing there?
I mean, just trying to learn something.
No, I just. So what you doing there?
Yeah. I want to make you an easy question, okay?
Okay.
Because one of the things that always has puzzled me about stall Flutter is the name, okay? In the sense that it seems to me that it's called a stall Flutter because it's close to the stall line.
Yeah.
Okay, but your flow is not really separated because you have migration and all that. Okay, but all the mechanisms that you are explaining are mostly invested mechanisms in the sense that you have acoustic reflections, the pressure acting on the mouth shape and so on. But the separation is not playing directly a central role in the sense that to me you don't have a fully separated flow. Okay, is that correct or is a misinterpretation?
I think if you look at this plot is so even for cases that from my experience, we've always needed a little bit of this is not separation, it's a bit of radial migration that you would get because you're going to create a pressure gradient going up the blade. No matter how bad is your mode, you need some form of viscous effect to get it going, okay. And this is a bit we do not get very well. So if you can delay this sort of migration, you would be in this sort of domain that no matter how much you change your mode shape, the blade still would not flutter. But having said that, if you take the blade up there and attach a very bad intake, for the blade up here, those blades that are all stable, I can design an intake to make it flutter, to get a good reflection. So in a sense, I think to get the absolute point on the flutter boundary, you need to get your viscous effects correctly.
Yeah, yes, I mean, because that you have migration, okay? Yeah. Because you have a mild separation, and then when you have a mild separation because of the centrifugal forces, you get some migration inside the boundary layer because you are looking at what is happening very near the wall, okay, here. So you have some migration inside the boundary layer, but and probably that changes as well the pressure distribution, but your separation is really very small in the sense you are not seeing a massive separation. No. In the worst case, you are seeing a mild separation, okay, that creates that small, well, not small, that migration, radial migration, okay, but you cannot see a fully separated flow in those cases, okay, is what I meant, okay. It was an observation, okay. Apart from that is
yeah, well, as I told you, I think if you get the mean flow correctly, somehow the rest of the unsteady parts, I think, in my opinion, are all acoustic. There's not much viscous effect going on.
Yeah.
And they are all linear.
Yeah, the thing is.
My opinion.
Yeah. Okay.
All right.
Thank you, Mehdi.
Thank you.
Some other question? Maybe I have a very basic one actually. when you start to have a flutter in a real condition, is it possible to stop it, or by, let's say, decelerating the engine, or do you have some kind of hysteresis so that it's difficult to come back to the normal condition?
On an engine, I could not tell you really what they do. They probably unthrottle the engine. But on the rig, what they do, they usually open the downstream nozzle and move it to a lower working line. And usually that works quite well. They can recover from it. Because usually you can see some signals of vibration beforehand. So you are ready to open the downstream throttle during a test. I'm not sure what they do it on the engine, but on a rig, they're usually opening the downstream throttle, unthrottling it, and moving the blade to a lower working line usually gets rid of it. There's no, I'm not aware of hysteresis, really.
Okay, and I suppose that there are some sensors which are able to detect the very precursor of this kind of phenomena.
Yeah, when you do testing, usually place some Q light just upstream of the rotor here. So you can measure, I think you use that also for detecting rotating stall or other forms of aerodynamic instability.
Okay. Thank you. One more question?
Yeah.
No.
Okay.
Just let 1 or 2 seconds to react. No. Doesn't seem to be the case.
All right, I'll just give you one more bit of information why air elasticity is important while we're here. Can you see my screen?
Yeah.
All right. Usually, all the cases I showed you, it assumes zero or you input some mechanical damping, because obviously you got the blade root here, which sits in the disc groove. And as you get vibration, you start getting friction between this component and this component. And as a result of friction, what happens is you convert some of the vibration energy to heat. So it works like a damper. So I equal friction damper. So we can model it using this sort of model. In order to increase the efficiency nowadays, what people are using is what is called a blisk, where the rotor and the disc all are one component. So consequently, you can see that there is no friction allowed between this and that because they're one component. And for such scenario, air becomes the only source of damping. So for flutter, that means that as soon as you have flutter or it becomes unstable, the aerodynamics, you do not have any mechanical damping to fall on. It will flutter. When you're doing something like forced vibration, you don't have any mechanical damping anymore. You have only aerodynamic damping. Therefore, getting the aerodynamic damping correctly for a structure like this is very, very important because it's your only source of damping. My final point.
Okay, thank you very much. So if there is no more question or comment, so let's thanks again the speaker, and thank you again for the very interesting talk. It was really nice for me because I heard about the aeroelasticity, but now I feel that I know a bit more, and even if I'm not a specialist. So I suppose it was very interesting for most of the people. So I just to remind you that there will be a new webinar in the coming weeks. So you are welcome to attend our webinar.
Oh,
so
great.
Thank you again, and have a good day for everybody.
Cheers. Thanks very much. Bye-bye.
Let's see you again. Bye-bye.
Bye-bye.
Bye.
Bye, Mehdi.
Bye, Rocky. I talk
Bye.
Bye.
Talk to you soon.